I might have said that my last video on the rotating space station, if you want to see that playlist down below, I said that's going to be my last non-inertial reference frame video, and I lied. I'm going to do one more, and this might be lied too, but I think I'm done because I want to really get on to the next big thing. So I remember two places, actually both of them were in Illinois. One was the main building at Fermilab. So if you haven't been there at Fermilab, they've got a really tall internal structure, and they have a pendulum hanging down, and it swings back and forth. And another one was at the Museum of Science and Industry in Chicago, and they have a pendulum like this too. So the idea is if you get a pendulum and let it swing back and forth, and you leave it alone, over the course of a day, the thing rotates, and it shows that the Earth rotates. Take that, flat earthers. So I want to go ahead and model this, and it's really, the math of this is not super easy, but let me just explain what's going on. Okay, so that's the Earth. Okay, so the Earth is rotating with an angular velocity omega, which we know, about 2 pi radians per day, but not exactly. So if you're over here in this location, and you let this swing back and forth, as the mass moves back and forth, well, there's a Coriolis force on it, and that depends on the velocity. So that Coriolis force is going to slowly make the thing move, and so it's not going to swing in the same direction over the course of a time. And you can actually calculate the angular velocity that it turns in direction. I'm going to call that omega p for the angular velocity of the pendulum. It's the angular velocity of the Earth times the cosine of theta, where theta is the co-latitude. And I don't know why we always use co-latitude, but the co-latitude. So for me, I'm at a latitude of 30 degrees, my co-latitude 60 degrees. Okay, let's just get to it. So we have a bunch of stuff, and so one of the derivations of this is kind of difficult because pendulums are difficult. So let's make a simple 2D pendulum first. Okay, so imagine that I have a pendulum, and I'm not going to go over this. I have a video about how to determine this if you want. I'm going to reuse the angle theta. I guess I should use phi. So there's some angle phi and length L, and there's a gravitational force mg on there, and there's a tension pulling that way. So if you release this from rest and theta is small, then this is just simple harmonic motion. Okay, so for simple harmonic motion for a pendulum, we get the angular velocity is 2 pi times the square root of L over g. And again, I'm not going to derive that. Now, if I have a mass on a spring constant k, that will oscillate back and forth also. And that will have omega is 2 pi square root of m over k. Right? So you know that. I mean, I'm not going to derive those things. But this is a grown-up class. I'm not going to derive those things because I've done it. And if you really want to and you can't find it, just comment down below and I will find it for you. Okay. So is it possible, instead of having this thing swing back and forth and dealing with the angle and the different tension and the gravitational force, could I just model this as a mass on a spring? And yes, I could. Instead, I could just say, okay, there's some spring force pulling this back this way and has a magnitude Fs is negative kx. This is the x direction. And k, okay, I can say up here, L over G is equal to M over K. So my K effective is going to be equal to mg over L. Okay, so I can turn my pendulum into a mass on a spring. And why do you care about that? Why do I care about that? The reason is that now suppose I want the pendulum to be, and I'm doing this as a small angle, right? Small angle. I want to take a pendulum and let it swing back and forth in more than one direction, in this case the xy plane. So z is my vertical direction. If that's the case, if I look at my xy plane right here, and then my mass is right here, I can just model this as a force F equals negative k r. So r is the vector position of that, and then I have negative k. So I have an actual force on that thing, which is useful, right? Let's do this. Let's show that these two things are the same in one dimension, and then I will do it and then we'll go ahead and do the Foucault pendulum. So let's program this, and if we have to delete it, we can delete it. I'm not going to do a super advanced study right there. So let's switch over to Python and show that this is actually the case. Okay, so here we are in WebVPython. Let's make a graph. I'm not even going to give it a title. F1 equals G curve. I am going to give it a color. Curve, color equals color dot blue. And I'm going to model the motion of a pendulum. So I didn't even show that calculation, but I'm going to do it. Let me switch back to the board. I'm going to show you how I'm going to do the pendulum because I've done this before. And again, I'm skipping some steps here. Okay, so that's important right there. So I can say that phi double dot is equal to negative G over L sine phi. Right? That's my equation of motion for a pendulum. And you can find that out pretty easily by looking at acceleration in the phi direction. And so if I know phi double dot, I can calculate phi dot. So phi dot 2 is phi dot 1 plus phi double dot delta t. I'm breaking it into small time intervals. And then I can calculate phi 2 is phi 1 plus phi 2 dot delta t. So my normal numerical calculation, and that's my pendulum. And then I can redo the same thing with using a spring constant of force like that. Okay, that's what I'm doing. Sorry about that. Okay, so we need some constants here. L, I'm going to make it pretty long, 5 meters. G is 9.8. M is 1. I don't even know why I picked that. So now I do need some initial conditions. So phi is going to be equal to, let's say, 3 degrees. So 3 times pi divided by 180. Phi dot is my initial velocity, 0. T is 0. dt is 0.01. Let's just say while t is less than 5. I'm just picking a value. So now I'm going to calculate phi double dot. So phi dd dot equals negative g times sine of phi divided by L. That's that on there, right? Phi dot equals phi dot plus phi double dot times dt. And then phi equals phi plus phi dot times dt. And then t equals t plus dt. I'm going to go ahead and plot, and again, I didn't label anything just because I don't really care. F1 dot plot t and phi, just so we can see that it's kind of working, and then we'll plot x. Okay, that's fine. So now I'm going to plot this as x, because that way I can correlate it to the other way. So let's call this xp, the pendulum plot. So if you look at your pendulum, which I don't have up here anymore, I'm looking at the x component, so that's going to be L sine phi. xp is going to be equal to L times sine of phi. And so let's plot this xp. Okay. So there it goes, back and forth. Yes. Okay, now let's do the same thing. I'm going to say k is equal to, what did I just say? M times g divided by L. And then I need x is going to be equal to, let's give it the same x value. So that's going to be equal to L times sine of phi. And then I need the initial velocity of 0. Okay, so then down here, I'm going to do my normal calculations. Let's do it right after this. So f is going to be negative k times x. V equals v plus f times dt divided by the mass. X equals x plus v times dt. And then up here, I need a new graph. F2 equals g curve. Color equals color dot red. And then I can plot that. F2 dot plot x, t, and x. So what I want to see is these are the same motions. And they're right on top of each other. So good on that. Okay, I'm going to delete all that stuff. And now let's make a 2D pendulum. It's just a 2D pendulum. Okay. So a 2D pendulum, now I'm going to make an actual graph. G1 equals graph. X, I'm going to make a trajectory plot. X tidal equals x, y tidal equals y, width equals 400 height equals 200, which is wrong, right? Because if you're doing a trajectory plot, you want equal dimensions, but I don't really care. Okay, so that's all the same. I don't need the phi anymore. I'm just making a graph. So I do need x. I can just pick an x. And in fact, in this case, I want to make a 2D plot. So I'm going to start off with some position. I'm going to say r is going to be the vector. I'm going to use vectors. Let's say it's 0.5, 0.50. So that's a half a meter, right? So that's a pretty big swing, but it's a 5 meter long pendulum, so it's actually still a small angle. My velocity is also a vector. V is going to be vector 0, 0, 0. I have k. Okay, and I'm just modeling the motion. So down here, and let's do this. Dot equals true. It'd be fun. And then I can do this rate 100. So I can model it in real time. So I'm going to get rid of that stuff. And I'm going to say f is negative kr. Now notice what happened there, right? Because r is a vector, and I multiply by k, so now force is a vector. So I have a 3D problem already. This problem is the same right now, but velocity is a vector, and I add in a vector. I do need to change this one. So that's going to be r equals r plus v times et. And then I need to plot something. I don't want that. So I said it's going to plot the trajectory. So let's plot the trajectory. R dot x, R dot y, and let's just see what happens. It's taken a long time to swing back and forth. There it goes. Okay. So I gave it some initial thing and it's swinging back and forth. That seems to work. Yay. Okay. Now let's jump back to the board real quick and talk about the Coriolis force and why we're not going to do the centrifugal force. So I guess I'm done with all that stuff. So in the rotating reference frame of the pendulum, I actually have the net force is going to be this. It's actually complicated, right? It's going to be equal to, well, I kind of already have trivialized it into a two-dimensional problem. So I can just call this F spring. I'm not going to worry about the tension. I'm not going to worry about gravity. I've already essentially taken care of those. And then I have the Coriolis force. And then technically I have the centrifugal force. So the centrifugal force is going to be m times omega cross r cross omega. And the Coriolis force is negative 2m omega cross v. So this one, in fact, I'm going to not include in my calculations because this just depends on the position. And really the position doesn't change. Okay, yeah, it's moving, but 0.5 meters, and that's the vector from the center of the Earth to there. Okay, so it doesn't change. Now, and there is a net force in that direction, but in fact, your pendulum's going to be lined up already with that included because that's what we call the vertical, right? That's the effective gravitational field on the Earth. We include that centrifugal force. So I don't need to model that. I just need to model this. So I need to find omega in my reference frame here. So that's omega right there. That's right there. I can redraw omega right here. And this is the angle theta, my colatitude. So I can say omega, let's call this omega e is the magnitude of the rotation of the Earth. So this is going to be equal to the x component, 0 x hat, right? Because x has in and out of the board. It's actually into the board. No, yeah. But it's not in any component in there. The y component is going to be right here. That's going to be omega Earth sine theta. And then the z component is going to be plus omega Earth cosine theta. Okay, so I can find that vector. And then I can take the cross product with my vector in the xy plane. Let's just go ahead and do it. It's not that bad, right? Now, don't worry. We're going to get some little bit of bad stuff in order to be able to measure the rotation rate, but we'll deal with that in a second. Okay. So I need to calculate omega e. Omega e, I'm going to call, oh, I didn't even switch. Sorry. I'm going to call it omega e. which is we, right? So that's going to be 2 times pi divided by a day, which is 24 hours times 3,600 seconds. Now I can calculate the omega vector. I'm going to call it just capital omega. It's the vector 0, WE times sine of theta, which I didn't put, WE times cosine theta. So theta is 60 times pi divided by 180. And that's for my location. You can change that. So down here for the force, I just need to add that Coriolis force in there. So let's do that. It's going to be minus 2 times cross omega v. That's it. That's it. Let's run it. And nothing happens. You're not going to see anything, right? Because this is in real time. This thing takes a long time to move back and forth. So let's just go ahead and ramp up the velocity, the rate. Okay, I already know I need to do that. So let's run this for, let's say, 5,000 seconds, and let's have this as, let's just make it super fast. I don't even know if that's a good value or not. Let's just try it. Okay, so it's oscillating back and forth. Is it rotating? I think it is. Yeah, it is. You can see this little bar is thicker up here than it is down there. So it takes a long time. 5,000, that's like not even 2 hours, right? 1 hour, 3,600 seconds. So it's under 2 hours. But in that time, it does indeed oscillate. I could probably turn off the marker. Let's try turning off the dot. See if it runs faster. Okay, yeah, it's getting wider. So it seems to be working. Now, I do have one problem that I know about. So watch this. Let me go down here. Let's run this for just an hour. Not an actual hour, that would be boring. And then at the end, I'm going to print R. I'm going to print the final position. And we have to wait. And I could make my time step bigger, right? I'm using a time step of 0.01. However, that time step matters over the course of one swing, right? So if I'm afraid to make that too large, or I might lose some stuff. So I'd rather just wait and be patient, and we can have a discussion while we're waiting. So it's not a big deal. How are you doing? I'm doing fine. It should end, hopefully soon. Hopefully. This is the part where I start questioning my choices. Maybe I picked T too long. Maybe my rate is too small. If I stop it and start over, I'm gonna have to waste everything I've already done. That does look pretty nice though. I mean, if you want to watch a Foucault pendulum over real life, you got to wait a long time too. So it's just like a real Foucault pendulum. I'm really getting ready to stop it. It looks, did it even stop? Okay, I'm going to stop it. I'm going to do it. Here I go. It looks like it's working though. Stop. Okay, let's make this just 1,000. Maybe it didn't print. Print R, yeah. That should be, ugh. Now I got to wait a third as long as I didn't wait. So it could have been, oh, you know what I should do? Let's add a 0 right here. I don't know if it can go any faster, but I'm going to try to make it go faster. I think it's doing that. There it goes. Okay, so you see the problem here is that there is a z component. I started off with the z value of 0, and there is a z component. That's just based on the Coriolis force is going to push it upwards, and I don't want that to happen. I don't think it's going to matter too much. But over here, I'm just going to go down, when I calculate r, I'm going to say r dot z equals 0. Right? So I'm forcing it into the xy plane. I'm saying you can't do that, although technically it could. Okay, so there. We're good. Now what I want to do is to somehow measure the rotation rate. Now this is kind of tough, right? I could just plot the angular position of the thing, but what I want to do is I'm going to take, and this is just what I did, And I think you could find other things. I'm going to take, let's make another graph. G2 equals graph, X title equals time, Y title equals angle, I guess. I want to find what angle it's rotating at. Okay, so I'm going to take the mass when it's near the origin. So when r is very small, and I'm only going to plot points there. Otherwise, I'm going to get too many points. Oh, I need a width here. I can't spell it. Height equals 200. Okay, so down here, I'm going to make a graph. But to make that graph, I'm going to say if the magnitude of r is less than 0.01, right? So only when it's really close to the origin, because it has a 5 centimeter thing. So it's only when it's less than a centimeter, then we can plot that. And what I want to plot is just, let's say, is that what I did before? Yeah, let's just try this. So it's going to have an x component of velocity and a y component of velocity. So let's just plot t theta equals a tan the y component, v dot y divided by v dot x. And then I'm going to plot a point, only if it's in that condition. So f2 dot plot t theta, maybe. And let's not plot this other one, because I think that's just going to slow things down. If that doesn't work, I'll just do what I did before. Okay. So it didn't run for very long. That's fine. So let's run this for 10,000 seconds. So the angle's increasing, but we don't want it to keep increasing forever. It should level out. Please level out. Don't be a straight line. My mind feels like it's leveling out. Oh, it didn't go long enough, huh? Okay, let's just do what I did before, because what I did before. I said, I'm going to just copy this, because I don't want to, since it takes so long to run. This is what I did before. I was trying to do something cool. So I said, if the magnitude's less than 0.02, then plot. And so what I did here is kind of weird. Oh, and if the velocity is positive. So I want to go one way. Otherwise, you're going back and forth both ways, and so it doesn't really help. And so I tried to do like a dot product with the x direction, but I could have just done v dot x. So I don't know what I'm doing. But let's just plot this anyway, and I called this f2. So let's run this now. And let's see if it levels off. Okay, it is bending. I can tell bending. I can see a bending. I did 55,000 seconds before. See? Okay, so I do need to go for longer. So let's go for, this is 10,000 seconds. So let's go for 55. And let's add another 0 in here, even if it matters. I don't even know. I guess I could turn off the rate completely. But that's fine. Okay, so there you can see whatever velocity angle is indeed changing. And I really want that part where it turns back, because that's a quarter of the angular, that's a quarter of the period, right? So I'm getting a quarter of the period right here, somewhere around 2.14 times 10 to the fourth. So let's calculate a quarter of the period from our theoretical calculations. So down here, a quarter of the period would be, let's call it T4 is going to be equal to the angular velocity of the Earth. See, wait, what did I do before? I need to switch. I'm having trouble thinking right now. Let's say, switching back over here. Where's my chalk? Okay, back to the board. Okay, so how do I calculate that? Where's my stupid chart? There it is. Okay. So I want to calculate this right here, but I want just a fourth, the time for a fourth. So omega p is going to be over a 4. No, wait. Omega p, no, T4. T over 4 is going to be equal to, no, let's see, omega p is going to be the angle, which would be pi over 4, right, a fourth of the way, divided by the time, t over 4. T4, I call it T4. So T4 is going to be equal to pi over 4 omega p. Is that right? Okay. So let's print that and see if we get the same thing. So T4 is going to be equal to, what did I just say? Pi over 4 omega p. Pi over 4 times omega p. Did I calculate omega p? Let's do it up here. Omega p is going to be equal to omega earth times cosine of theta. Yeah. And let's print that. T4 equals T4. Okay. Let's try taking out this rate statement, see if that helps. See, now it's not going to show anything until it's done. Okay, it did it. Okay, so we get 2.16 times 10 to the fourth, and so that's, yeah, it looks like, you know, oh, you can't even see that. It looks like it could work, right? I mean, it's somewhere around there. I mean, I didn't get the exact thing. I did a plausibility argument. If you want to play around to make the code better, to make the plot better, that's cool. But the point is that we did model a Foucault pendulum. We did show that the rotation of the pendulum depends on the rotation of the Earth, and that's cool enough for me. So hope you like that. I'm done. Code down below. I'll talk to you later. Bye.